All right, what we know so far, we know this is integral sign. We know this is a lower limit. We know b is the upper limit, and we know this is the function to be integrated. And with respect to variable, if we had a variable up here, if this was x up here as the upper bound, could the variable inside the integral be x then? No, it has to be something else. It has to be t or whatever. It's usually t. All right. So we know that so far. Well, let's go some far. Let's kind of review again. Definite integral as area. Remember, let's set this up as our limit. This area is the same thing as the limit as n goes to infinity of the sum I equals 1 to n of f of, and I use c sub I this year. You could have x sub I or c sub I. And then we had delta x, correct? And then we knew how to find the c sub I and the delta x. Limit n goes to infinity, sum I equals 1 to n, f of a plus b minus a over ni, and then b minus a over n out here. This is pretty much fundamental, guys. So make sure you know this. There's always going to be a question, something like this, connecting these two on the AP test. All right. Connecting those areas to common geometric figures. Okay. Now, if we look at this one, a couple of us were struggling with this a little bit, so I thought I'd go over it again. If we had to graph this, this is the function 4, which is a horizontal line. Okay, so we have a function 4. And we need to find the area from 1 to 3. So from 1 to 3. 1, 2, 3. That means we're finding the area of a rectangle, right? Okay, so what would the area be? Well, 2 times 4 is 8. Width is 2, height is 4. 2 times 4 is 8. And that'd be unit squared, obviously. Okay, I gave you guys a worksheet that had a linear function, x plus 2. We gotta be able to remember how to graph these lines. 2 is the y-intercept. Some of you guys listed it as the x-intercept on your worksheets. I saw that. Slope is 1. Up 1 over 1. Up 1 over 1. Up 1 over 1, right? So that'd be 2 and then 3. So that'll be our line right here. And obviously it goes off this way too. We just want the area from 0 to 3. Now, because the y-intercept is not 0, we have a trapezoid now, right? Okay, so this area would be then 1/2 our height, which is the interval width, 3. Base 1 would be what? 2. Base 2, that's 5. So what would that be? 5, 6, 7 times 3 is 21 halves. And then obviously unit squared if we wanted to. Now what about C? What's the geometric figure that C makes? It's actually an iteration of this. What is this? That's a circle. Okay, now let's solve for y. Y squared equals 4 minus x squared. Take the plus or minus square root. But they only give us the positive one, right? So that would be a half circle in the upper section above the x-axis, okay? It's not shifted left or right. We have no h and k up in here. So we'd have radius of what, 2? And that's why they have positive, negative 2 as your upper and lower bounds. And so it looked like this. And so we have that half circle, so area of a circle, half of it, so 1/2 pi r, which is 2. And then would that be 2 pi? Again, unit squared if we're talking about area. All right, just refreshing our brain on this Monday after a nice weekend, because we were not thinking about homework, were we? We're outside enjoying life, getting some fresh air. Okay, you don't have to copy these down. We should already know these. Okay, if we have the integral from a to a, that's always going to be 0. And then again, if we need to flip the bounds, put a negative out in front. Okay, real quick then, what do I do with this one? Well, if I want to flip the bounds, and I know I need to because the upper bound is bigger than or smaller than the lower bound, remember, put a negative sign out in front, and you go 0 to 3, and then we need to use parentheses, and then dx. Okay. So we know that already. We know we can break up the bounds. Okay, just like we did adding parts of areas together, we can rewrite our integrals that way. Okay, enough reviewing. Let's get on with the show. Well, the fundamental theorem of calculus, or FTC, as the cool kids call it. And this is the fundamental theorem of calculus. This is what connects differentiation with anti-differentiation. And it has to deal with the definite integral. If you look, if a function f is continuous on the closed interval, that's important. If your function is not continuous, we cannot use this. And capital F is an antiderivative of lowercase f, like we looked at before, on that interval, closed interval, a to b. Then, if we have this antiderivative, this integral from a to b of f of x dx, it is simply the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound. That is all it is. That's all we have to do to calculate this. We've already talked about the integral as area. We've talked about the bounds. We've actually calculated antiderivatives. So today should be fairly easy. You're finding antiderivatives and you're evaluating those antiderivatives. Okay, last week we just found them. Today we're evaluating our antiderivatives. All right, now let's actually do a couple problems. These are fairly easy. Okay, evaluate each definite integral. We're going to learn a couple things along the way. We're going to learn a little bit of a new notation that maybe you've seen in your ventures watching YouTube videos because you're halfway paying attention in class. All right, okay. Right now, ignore the bounds. Let's find the antiderivative. What's the antiderivative of x squared? Okay, good. What's the antiderivative of negative 3? Minus 3x, right? Because technically this is x to the 0 power, would be 1, and then you add 1, and then you divide by 1. And then what? Plus c? Okay, plus c. Now watch this. This is the antiderivative. Now we need to evaluate it from 2 to 1. This means we're evaluating the antiderivative from 2 to 1. Now, you can use the end bracket. I've also seen people, and I do this sometimes too. Whoops. And then put a 1 and 3 like that. That means evaluate. Because remember when we did our derivative, sometimes we'd say evaluate the derivative at like x equals 2 or something like that. Remember that? Okay, so it's very similar, except for we just have bounds, upper bound, lower bound. All right, now what we do is evaluate the antiderivative at 2 and then subtract the antiderivative at 1. So it'd be 1/3 2 cubed minus 3 times 2 plus c minus parentheses 1/3 1 cubed minus 3 times 1 plus c. Okay, what would that be? What, 8/3? Minus 6 plus c minus 1/3 plus 3 now minus c. Well, look what happens to the c's, guys. Those arbitrary constants, they always cancel. So when finding a definite integral, when evaluating a definite integral, you do not have to put plus c anymore. For definite integrals, you do not need to put plus c, because why? We found out it's always going to cancel. All right, would that be 7/3 minus 3? Well, 3 is 9/3, right? So 7/3 minus 9/3 would be negative 2/3. Now, if we just have to evaluate this definite integral, just leave it as negative 2/3. If there's some type of story problem or whatever, you could use maybe unit squared or whatever, if they want it as area or as an amount. Like we learned today also, this could be a rate. The antiderivative of a rate is an amount. This could be an amount of money you lost or whatever in crypto right now or something. It's just taking a hit. All right. Again, rewrite if necessary. 1/4, 3x to the 1/2. I think it's really important to take that 10 seconds, rewrite your antiderivative so you can visually see that a little bit better. So it's just add 1, right? So you know how to do that better. Okay, 1 plus 1/2 would be what, 3/2? Multiply by the reciprocal, and that's just 2, isn't it? We don't have to put plus c anymore if we're evaluating a definite integral because we're doing something with it still. 4/1. So we got 2, 4 to the 3/2 minus 2 times 1 to the 3/2. And for some of you guys were asking or thinking to yourself, could I factor out a 2 and evaluate this from 4/1? Yes. I typically don't on these problems. All right, 3/2 without a calculator. So that'd be the square root of 4, which is 2. Now cube 2. That's 8. And then 1 to any power is just 1. So that'd be 2 times 8 is 16. 16 minus 2, 14. Are we okay so far? We can fix that. Okay, folks, what is the antiderivative of secant squared? Tangent x. Now, do I have to put plus c? Nope, because we have a definite integral. We're doing something with this still. We're evaluating this definite integral from 0 to pi over 4. Pi over 4, 0. So we have tangent, pi over 4. That should be very easy. Minus tangent, 0. Now remember, tangent sine over cosine, right? We know at pi over 4, sine is root 2 over 2. Cosine is root 2 over 2. So tangent of pi over 4 is just equal to 1. Minus tangent of 0. Well, sine of 0 is 0 because the height is 0, right? And then cosine of 0 is 1. So 0 over 1 is 0. Cool thing about these guys is you can use your calculator to check your work. However, you don't have a secant squared button, so you got to be able to type that in correctly, right? 1 over cosine x quantity squared. That's why you have to type in secant, or secant. Okay, questions on this so far? I think it's pretty easy, right? Because we've kind of built up the steps to get to this point. Something we haven't really talked about too much is absolute value. The problem with absolute value is it takes sometimes negative values and makes them positive. Where is that breaking point for absolute values? Or you could think about, what have we done with absolute values in the past? What x value have we found in the past for absolute values? Yeah, when absolute value equals 0, that helps us break up the derivatives. Remember that? Okay, same thing here. Find out when the absolute value equals 0. And that's going to be our breaking point on our interval. So that happens at x equals 1/2. That x equals 1/2 is on the interval from 0 to 2, so we have to break up this antiderivative to actually take the antiderivative. Because we do not know how to find the antiderivative of absolute value without a calculator if we don't break it up. Okay, this goes from 0 to 1/2 now. Now, the whole idea of breaking this up is so we don't have to have a absolute value. For values from 0 to 1/2, what do you know about the inside's absolute value? From value 0 to 1/2. The inside's negative, isn't it? So that means we have to have that negative to make the value positive on our absolute value. Plus interval 1/2 to 2. Now on the interval 1/2 to 2, that's positive, so we don't even need the absolute value sign, right? Okay, so 2x minus 1 dx. All right, this is how you have to handle absolute value antiderivatives by hand. If it's a calculator part of the problem or a test or whatever, just type this in your calculator. It takes 2 seconds, right? All right, negative can go out in front, or you can just distribute. It's up to you. I don't care. Antiderivative of 2x, that'd be what? X squared divided by 2 would be 1, and I'll keep that negative along with it. Now I'm going to distribute the negative, so plus, and that'd be what? X, right? All right, I'm going to go parentheses, evaluated from 0 to 1/2. Plus, this antiderivative would be x squared divided by 2, that'd be 1 minus x, evaluated from 1/2 to 2. All right, so we have negative 1/2 squared plus 1/2 minus 0. Plug in 0, it's 0 for both, right? Plus, okay, let's see here, 2 squared minus 2 minus 1/2 squared minus half. Go through this. So it would be the power first, be 1/4, and negative, so negative 1/4 plus 1/2 minus 0. 4 minus 2, 2. That'd be 1/4, so negative 1/4. And then plus 1/2. All right, a fourth minus a fourth is negative 2/4, which is negative 1/2, which will cancel another half. So we got 2 plus 1/2, 5 halves. Is that what you said? All right, a little bit of work, a little bit of thinking, follow the procedure, it's the same thing every time. Any questions on this so far? All right, here we go. Give that one a shot, please. You guys getting 1/2 x squared evaluated from negative 3 to positive 3? So the 1/2 3 squared minus 1/2 negative 3 with parentheses this time squared. That's 9 halves. Minus, that's 9 halves. Ooh, sweet. 0. check this out though. Like, this is the positive area. This is that negative area. There's another one. What'd you guys get? 24. Okay. All right. Let's see how you did. Okay, that'd be x squared divided by 2, which is 1. Evaluated from 5 to 1. What? 25 minus 1. That's it. Okay. Not too bad. Am I going too fast for Monday, or are we all right? So. What in the world is going on here? Okay, that'd be what? 16 minus x squared to the 1/2, right? What do we have here, guys? What type of function is this? A what? Another circle? This is a full circle? Half circle. Do we have a way to anti-derive this right now? This is a composite function, kids. Have we done anything with composite functions yet? There's no way for us to anti-derive this right now. So if you get a problem where you cannot anti-derive it, you have to think about it graphically. Okay? And so again, I think we just did this one, didn't we? I was close to it. This would be that half circle. And we want you to recognize that as a half circle. Find that area. It's going to be positive. So just write it out. 1/2 pi. Radius is 4 squared. What is 16 divided by 2? 8 pi. There we go. So this is kind of like a trick one where we can't anti-derive this analytically. We have to think about this graphically. Find the area. They mean the same thing. All right, one more. 3 minutes. You have to do it in 2 on the AP test, 1.5 if you're lucky. Absolute value function. What do we do? Do we break it up? How do we break it up? How do you write it? Where are you guys breaking this interval up at, guys? 0. Yeah, definitely. -2 to 0. Now from -2 to 0, the inside is negative. So I do have to apply the negative. Plus antiderivative 0 to 4. No absolute value needed. In this case, we have what? 3/2 x squared minus evaluated -2, 0. That'd be 3/2 x squared evaluated 4, 0. Okay, if we plug in 0, we get 0. Minus, I should say. Minus, okay, that'd be -3/2 -2 squared 4 to -6 negative, so +6. Plug in a 4 and then plug in a 0. All right, be 16 divided by 2 is 8. 24. Final answer 30.